Okay, welcome again, everyone, to the seL4 Summit, and it is my pleasure to introduce our first keynote. Professor Gernot Heiser, thank you for being with us. Gernot, of course, probably needs no introduction, yet I will do it anyway. Gernot is a Scientia Professor and John Lyons Chair of Operating Systems at UNSW Sydney, and his research interests are operating systems, real-time system security, and safety. He also leads the Trusted Systems group at UNSW, which pioneered large-scale formal verification of systems code, including, of course, the seL4 kernel. He's also the founding chairman of the seL4 Foundation. And we are happy to have you speak to us today, Gernot. Thank you.
Good morning. Good morning. It's great to see the room full of people. It's a great feeling to be among the community. And we've got about 70 people here. It's a sellout crowd. And we've got more people participating online. So hello, rest of the world, including about a dozen people in the lab in Sydney watching this. Hello, Sydney. Great to see you. Right. So I've been asked to talk about what's going on with seL4 in research, and obviously in particular at the Trustworthy Systems group in Sydney. And well, seL4 has been a huge success story. There's no doubt about that. And so what made it really famous is summarized in this diagram, which represents the verification story. So we were the first ever in the world to verify an operating system kernel. That was massive. But amazingly, even 13 years later, seL4 is still unique. There's no other verified operating systems, I would say, with one exception. They're all toys. And still, none of those other systems is a capability-based system. So they all took the easy route out, and it's so much easier to verify something where you just don't have a principled access control model. Capabilities is what gives you the power we need for security, but it's also part of what makes life hard. So we're still unique just in this point. We have now a verification story across 3 architectures, 2 of them complete. H64 is happening. And seL4 is not only unique in terms of its verification story, but also it's unique in terms of its resource control. There's no other system that I'm aware of that has a real comprehensive principled control of all systems resources, which at the microkernel level basically means time and space. And in terms of time, that was part of the original setup. In terms of, space. In terms of time, that's been added later on. This is the famous MCS kernel, which is actually mostly the work of Anna, who is sitting here in the audience. And that's a real big step forward. So in terms of operating systems design and implementation, seL4 really has 2 significant contributions. The first one was its story about managing spatial resources, and then the second was managing time. And time is still where a lot of the work is happening. It really is the final frontier, because arguably we sort of solved the space problem with seL4. We haven't quite solved the time problem, but we are at it, and we are getting close, and we're far away of anyone else. So what does time mean in context of the microkernel? There's really 2 aspects to time. The one is an integrity issue, that if you have a trusted and a less trusted domain, then potentially execution of the less trusted domain can interfere with the execution of the trusted domain, and in the worst case, force it to miss deadlines. And obviously, that's what you want to avoid. So that's an integrity issue. And the other is a confidentiality issue, where the execution of a trusted domain holding secrets can affect the execution of an untrusted domain that's not supposed to have access in the secret, and through that leak secrets. And that's the confidentiality issue of timing channels. And we're looking at both. So the first one is the integrity issue, which, as I said, Anna's MCS model made a huge step towards solving. This is the idea that we have capabilities for time. these are our scheduling context capabilities, where you can only get access to the CPU if it's explicitly authorized with a capability. And that access can be transferred. If you invoke a server, then you can loan that time access to the server, and that server then executes on your behalf on your time budget. And when the execution finishes, the rest of the budget is returned to you. So that introduces a very strict accounting that is essential for reasoning about timeliness, in particular mixed criticality real-time systems. So this was a really big step in treating time as a first-class resource, and including the ability to restrict access to CPU time to high priority jobs. And that's really critical in mixed criticality systems, because you have things of different criticalities operating at different time scales. So a typical thing is you have some control loop which operates at physical time scales, so milliseconds. And then you have Ethernet or other networking that need to be serviced quickly. So it has to have the ability to preempt the critical operation. And you need to allow that while still guaranteeing enough time to the less critical operation. And this is enabled by this scheduling context model of the MCS kernel. The question is then, okay, what happens if the budget runs out while in the server? If you don't do anything else, that would block the server for anyone else. And of course, that defeats the principle of temporal isolation, which you really need for mixed criticality systems. And the existing MCS model has a mechanism for that. It's timeout exceptions. So if the server runs out of budget, it gets an exception that can be handled. But that means it's typically, if the server is stateful, that is a complicated process of resetting it to a defined state. And that forces extra complexity on the server. So one of our present activities is looking for ways to remove that complexity from the server and go back to allowing really simple servers with minimal policy, and in particular, don't forcing a multi-threaded concurrent design on the servers. And the idea there is to introduce a budget contract between clients and servers. So we have a threshold value, and the client is only allowed to enter the server if it has enough budget left to get through the server's execution. And the flip side of that contract is the client can be assured that the server will not use more than that budget, that threshold value of its budget. So it gives a two-way protection. And the result of that is, in normal operation, the server does no longer have to worry about running out of budget. And that's important because running out of budget is not it's not an error case, right? It's sort of a normal thing because the client doesn't really have a lot of control over its budget. And having a mechanism that enables the server to ignore this sort of routine case of low budget is important for simplifying the server design and making it easier to reason about timeliness. And as I said, it protects the client as well. And so the idea is we have this threshold, and if the client has not enough budget to enter the server, its remaining budget is below the threshold, it gets suspended until it has accumulated enough budget and then can enter the server, and we know it will go through. And the way this is done is the threshold becomes an attribute of the endpoint that's used to invoke the server. And we're at the moment, I've got a smart undergraduate student on this. We're working through all the details, and I think we're pretty close to having the model finished. So this is going to pop up as a request for comment for community feedback pretty soon, probably in the next few weeks. So this is sort of if you like, an incremental improvement on the model, but it's really important for the ultimate goal, which is to formally reason about timeliness in an overall system. So this is the upcoming challenge, which I really want to address is to be able to reason about timeliness of critical components in an overall mixed criticality system. That work hasn't started because we need a few things sorted out. In particular, the threshold value is really helpful for enabling this, and needs to be more theory, etc. So right now, we're doing the preliminary work. I'm waiting for a good PhD student to really take on that topic. So that's what's going on the temporal integrity side. On the confidentiality side, we have, as I said, the issue of microarchitectural timing channels, which are really result from sharing, from competition for shared hardware resources. And the question is, how can we control that to prevent any unwanted information flow? And those who attended previous summits will have heard me talk about the issue of time protection before. So this is the temporal equivalent of memory protection, which we use to solve that rather than the usual patch and pray approach, which pretty much everyone uses. It's actually frustrating, right? So when we first worked on this, first, I found it impossible to get any of the work published, because who cares about timing channels? Some military guys might worry about that. It's an exotic issue for special purpose systems. Show me a side channel and I take it seriously. And then Spectre came along. And of course, Spectre, it's often misquoted as using a side channel to get information extracted. It's not a side channel. It's an active Trojan leaking. The whole idea of Spectre is through speculative execution, you build a Trojan out of gadgets in innocent code. So even the code itself doesn't even contain a Trojan. It's constructed. And that uses this covert channel then timing channel to extract the information. And so Spectre, of course, is just one mechanism, but as soon as you run any unverified code in your high security domain, you have to assume there's a Trojan in there. So these covert channels really matter. So what's time protection? The idea is we want to be able to not only prevent these timing channels, we want to be able to prove that we can prevent those timing channels. And the approach of time protection is identify and securely partition all the hardware state that is the fundamental reason for the existence of these channels. And there's two ways to do that. We can either spatially or temporally partition. So spatially partition means you have to partition, for example, your caches. And this is using page coloring is an established technique that's relatively straightforward to apply for the lower level of caches in the hierarchy, the ones that are physically addressed. It doesn't work for on-core resources, because on-core resources are pretty much by definition not shareable. If you made all these partitionable, spatially partitionable, you basically create a second core. So it's inherent in the on-core state that it's not partitionable. It's also would not be hard without any specific hardware support, impossible to get that under operating system control, because all these on-core resources are virtually addressed and the operating system is not in control of virtual addresses. So the way out there is we need temporal partitioning, which basically means it's secure multiplexing. So the resources are allocated to one domain for a while, and then when it's switched, we need to reset it to a defined state that's independent of his execution history, and then the multiplexing is safe. Okay, so how do we do that? As I said, the spatial partitioning, it applies to physically addressed resources that are off-core, and it's relatively obvious how to do that, although I wouldn't claim it's a solved problem, because we have it's okay with caches. It gets a bit more difficult with memory. We're looking at that later. But for now, we're focusing on the on-core stuff, and that's where we need the secure multiplexing with the flush. So the idea is, this is a very abstract view of a context switch between partitions. We switch the user context, set the timer for the next time slice, expire, and then return to the user. And somewhere in that, we need to make sure that we get rid of any any history-dependent state. And so we flush the on-core state. The problem with that, of course, is the flush itself depends on that state. And that's mostly the L1D cache, which can have dirty and clear lines, and the dirty line is more expensive to flush. So the latency of the flush is history dependent, and we need to account for that. And we need to do some time padding to the worst case flush time in order to achieve this. Okay, so that's all okay. It's not that difficult to implement. We've done that a few years ago. My other recent PhD student, Tian Ge, did that, one best paper at URSS. And the question is then, okay, can we prove that this does the job? And if you want to do that, what do we have to prove? Well, first, we need to prove that all the non-partitioned hardware state is properly flushed, which obviously is not possible without having a suitable model of the hardware. And this is where assumptions come in. So we have to make an assumption that the hardware gives us the right mechanisms to do that. And I'll get back to that later. And at the moment, obviously, we need to abstract this somehow to make it tractable for the formal methods. And then the good thing is, even though we're doing this to reason about timeliness or lack of timing channels in the system, it becomes a purely functional property. We have to implement this flush correctly, which is a clear functional property. And then we need to prove that once the flush is done, everything is completely deterministic. And that means we need to reason about how does the rest of the code access cache lines, and is there any possible history dependence in those operations? And again, while this needs a model of the caches to reason about it, it's again a functional property. And as verifiers, well, I'm not a verifier, I'm an operating system guy, but I work with verifiers, and they understand very well how to verify functional properties, whereas reasoning about time is just very hairy. And then we need to prove that padding is correct. And this is where the word time in some way enters explicitly. And we can capture that by having an abstraction of a clock, where we just reason about clock ticks and padding to a certain or number of clock ticks executed. And then it becomes a functional property again. And this is where people in the verification team are actively working at, and in particular, Scotty, who is sitting there in the back, is one of the people, one of the two core people working on that project. So the status of this one, it's made a fair bit of progress since I talked about it first. So we have specified the isolation property we want, and on a high level, actually proved enforcement. And now we need to map that high-level model onto the actual seL4 model. And this is where the work is going on at the moment. So have been done, in particular, updating the seL4 abstract specs to make this, to basically define the target where we have to connect to. And then there's work in progress on proving that these actually do the right thing. And our hope is to have this finished in time for the SOSP conference deadline, submission deadline, which is sort of May-ish next year. So far we carefully, I'd say we might be on track. It's going to be a bit of a challenge to meet that. So this work, it has support from the Australian Research Council. It has in the past been supported by the US Air Force, the Asian Office for Aerospace Research and Development. And we also had support from UK's National Cybersecurity Centre. So this is all fine. But remember, as I said, this has to be done under certain assumptions. And in particular, we have to make assumptions on the behavior of the hardware. In particular, that the hardware has some sort of sanity which is required to do that. And this is where sort of the bad news comes in, because when we started implementing this, we found out this should work. But actually, when we measured the channels, it didn't. There were still remaining channels. And we dug deeper and deeper, and that detracted us for about 2 years until we realized hardware is broken, period. All the present processors that you can buy are broken. They're impossible, fundamentally unable to prevent timing channels. So how do we get out of this? Well, fortunately, there's this new kid on the block called RISC-V. And It has an open spec. It's got open implementations, including one open source implementation developed by ETH Zurich, which used to be called the Ariane processor. And that's a really nice test bed. And we have a student from ETH Zurich here who actually implemented this, and he'll give a talk later on explaining the details of that. So that's Neil sitting in the back who will talk this afternoon. And it turns out it's actually straightforward. There's no reason why this should not go into hardware, and it's making its way in RISC-V. Okay, so this is time verification properties. And the other thing that's sort of related to time in a way is multi-core. You may have heard that we have, or the Proofcraft people are making the first steps towards a verification of the multi-core model. It has only seed funding at the moment, so we're really looking for more funding for that. But before they get into that in earnest, we want to sort out some fundamental issues about how does the multi-core kernel really look like. You may be aware that so far our multi-core kernel has what's called a big lock. So basically you enter the kernel, you grab the lock, and you release the lock just before you get out of the kernel. If you tell that anyone outside the seL4 community, they think you're silly. Linux tried that 10 years ago, it didn't work. If you scale, it doesn't scale to more than 2 cores, etc. Of course, that's a completely incorrect comparison because the average Linux system call is about 3 orders of magnitude longer than the average seL4 system call, and that completely changes the ballgame. So this actually performs perfectly fine as long as you work on closely coupled cores. So basically your cache line migration latency between 2 cores must be well smaller than the system call latency. If it's not, then it's the wrong model anyway. So in principle, we can go with that. The problem is it really has some distasteful issues, particularly when you're interested in real time, because it's very difficult and inherently vastly pessimistic to bound worst case execution times in this model. And also it creates massive timing channels, etc. across core. So we're looking at trying to get rid of this big kernel lock by and resolve that obviously before the verification gets serious about verifying multi-core. We want to have them not deal with a moving target. So the idea is we're experimenting with a particular reader-writer lock, which we can call the bounded reader-writer lock. So this is my colleague Kevin Elphinstone, whose brain work that is, where most of the kernel does not have to be completely locked, but you just need to access a reader lock and combining that with some lock-free updates, we think we can keep the kernel mostly out of the lock. And of course, that's a nice boost in terms of certainly predictability of IPC performance and a few other things. And what makes this lock bounded is that the worst case latency a writer has to wait on the writer lock is the worst case execution time of one reader. And that's a nice low bound that allows us to work sensibly with. So this is actively being worked on. We have proved the desired properties of this lock implementation, implemented it on ARM and x86. And at the moment, James is working on integrating this with a version of seL4. So it's work in progress, but the aim of that is to have this finished by November. And then we can start evaluating it properly. This is supported by NCSC again, so they are really good friends of us at the moment, supporting a lot of our critical work. Okay, so this is sort of pushing the envelope in terms of the seL4 model, making sure that it's staying ahead of the curve, ahead of everyone else, defining the state of the art. Okay, we've already, but the work we're doing is sort of going in places no one else can even think about. The kernel as it exists is already vastly superior to anything else. So why isn't it everywhere? seL4 has seen a really good uptake in many domains, but it's nowhere dominant as it should be. So what's stopping that? And to my view, there's really these 4 issues: usability, functionality or lack thereof, the fact that trustworthiness means more than just the kernel, and getting out of just the embedded domain. Although I'd be very happy if we own the embedded space, but I think we can take it further. So let's look at those in turn. First is the usability issue. What does that mean? So we have you're not recommended certainly for building embedded systems on coding to naked L4. So we have this framework called CAMKIS, which gives you a nice component abstraction. And what it does is you define your system architecture using a formal architecture specification language that defines the structure, the architecture of the system, and then the CAMKIS framework generates the glue code to be able to link that into an overall executable. That's sort of pretty straightforward IDL. It does much more cool stuff. In particular, it maps this architecture spec onto a low-level spec called the CapDL formalism, which basically describes access rights at the low-level granularity of seL4 objects. And to give you an idea, there's basically an order of 2 difference in complexity of these 2 representations. So a trivial system that contains 2 boxes and a connection at the CAMKIS level translates into 50 or 100 seL4 objects. So that's a massive gain in abstraction. And from CapDL, we can then generate not only initialization code that boots the system in the state described by CAMKIS, but we actually have a verification story about that. So it generates a verified initializer that happens to be in the CapDL language that will get some mention later on. And that translation is provably correct. So that's a very powerful property. Okay, so why is that not good enough? Well, turns out there is some issues with CAMKIS. One is it's not an SDK. It forces the kernel build system on everything. So basically, when you build an app, you have to build the kernel with it and struggle with the kernel build system, which has a pretty high barrier to entry. It's very powerful and it's been chosen for really good reasons, but it's not what application developers want to bother with. The second is CAMKIS is totally static, and the static thing is totally ingrained into the design and implementation and would be extremely hard and costly. We had estimates in the past for just things like restarting virtual machines, and they were like several person years kind of effort. That's too rigid. And it also has overheads. So CAMKIS is good for assurance, but not good for usability. And this is where we are getting to the new kid on the block, which is the seL4 core platform, which is really a small operating system framework specifically aimed at IoT, cyber physical systems, etc., and other embedded use cases. And it has the same property as CAMKIS in the sense that it leveraged the verified seL4 isolation properties for building security into the system, but then it's way leaner. So it really does not cover up seL4's superior performance, and it retains a really small trusted computing base, small enough that we have hope in actually verifying this. And it provides an SDK, so you can use a kernel binary with a build system of your choice. So you can just use straight make, for example. Also, what I've seen in the past a lot is people using the seL4 primitives incorrectly, and I'll talk about that later on Wednesday in my talk. Because seL4 gives you a lot of freedom, it gives you a huge foot gun to aim at your foot, and CAMKIS retains most of that foot gun power. And it's not what you want to hand over to the average developer. So the seL4 core platform explicitly and deliberately constrains the model to make it sort of the natural choice to map correctly onto seL4. And we think TCP is small enough that it lends itself to a verification. And the details on that will be in Sultan's talk. I have not seen Sultan. I hope he's here. Oh, he's there in the back. Okay. So he will be talking later about the core platform and what we want to do with it. That work is also supported by NCSC. So that's the usability aspect. And in particular, it's actually, we found it straightforward to extend the core platform to more dynamic use cases. There is prototype implementations around which will start solidifying. Okay, next thing is functionality. We need more native services, and we need to make it easier to provide these native services. And the key component here is a driver framework. Drivers are always a huge pain point in any new operating system, and anyone who's worked with seL4 knows that, right? We need drivers, and drivers are difficult to do. People try porting Linux drivers. There's actually some really cool work later today by our friends from Capgemini on an approach to import U-boot drivers into a seL4 environment. That's fine, as long as you don't worry about performance and as long as your drivers are not part of your trusted computing base. So it's really extremely helpful, but with a limited ambit. We want to be more general. We want to be able to do drivers that are A, high performance, and B, trusted, trustworthy, verifiable. And so this is where the new seL4 device driver framework comes in. It's a model that makes writing drivers simple, but secure and really low overhead. And turns out we can do that. The idea is based on zero copying, transport layer as much as possible, standardized interfaces, a vastly simplified driver model that rules out a lot of the typical driver bugs by construction. And lo and behold, it actually performs. And Lucy will this afternoon give you all the dirt on that one. And it's really exciting, I think. So this work was initially supported by the seL4 Foundation, and it's now got a lot of support from UAE-based TII. Are any TII people here? No, there are. Well, quite a crowd, actually. Great to see you. Thank you very much, because this is really important work for the overall seL4 community. And then the next thing is trustworthiness. So we have a trustworthy kernel, but that doesn't give you a trustworthy system. And my group is not by chance called the Trustworthy Systems group. It's not the Trustworthy Kernel group, it's the Trustworthy Systems group. We want to build systems that are actually trustworthy and provide the tools for you to do it too. And that means, yeah, ideally you want to have your whole trusted computing base verified. And of course, this is where we have to talk about cost. Dollars matter. If you look at what the original seL4 verification did, it took produced almost 200,000 lines of proof, mostly handwritten, consumed 11 person years. That's a fair amount of effort for verifying 10,000 lines of code. And by now, whole proof base has well over 1 million lines of proof script. So that's a huge investment. And that's just mostly the kernel. And that was for code that was designed for verification. One of the things we learned is it's infeasible to verify code that's not written for verification. And of course, that creates a new challenge. It means you really have to understand what you do when you write this code. You have to have a fair bit of verification expertise, or at least very direct access to verification experts. And that's not what normal developers have. Turns out if you put that cost in context, it's actually not that bad. So seL4 was about $400 US, $2,009 per line of code, compared to a Pistachio kernel that was done earlier in a very similar environment, with sort of similar skill sets, etc. It's a factor of 2 to 3, so not as bad as you would think. Kernel code is expensive, verified or not. And it beats the crap out of non-verified things like Integrity, who will tell you they have a verification story. Of course, it's for a 20-year-old PowerPC processor and nothing else, and they can't really repeat it, etc. And of course, we outperform them massively, and we can actually change our kernel. They cannot if they want to retain that assurance. So we're looking at a factor of 2 or 3. We need to improve verification efficiency. And that's really important because in the end, we want to verify the complete trusted computing base, and that contains much more than the kernel. So for example, it contains the seL4 core platform. Well, Turns out that's just a few hundred lines of code. So if we can't verify that, then we should give up. As I said, Zoltan will talk about this. But then there are things like file systems and networking and network stacks. They tend to be 100,000 lines plus. Device drivers, well, they tend to be 10,000 lines plus. If in Linux, we can keep them to a few hundred lines of code and still outperform it. So that's a big gain, but there's lots of them. That's the challenge, right? And devices are basically commodities. You need to be able to have a repeatable process of verifying your drivers if you want that. And then you have obviously some core component, which is what this whole system is about. And so somehow we need to scale verification by at least an order of magnitude, but while reducing the cost. And the key thing there is something we pursued for a number of years is using better tools, high-level programming languages. So the idea is to simplify the job by using a more appropriate language than C, because in C you have to prove a lot of things which other languages guarantee you by the semantics. So this is the Pancake project. You may have heard of a predecessor project called Cogent, which in the end we buried about a year ago because it wasn't going anywhere, but we learned a lot of what not to do and what to do right. So we now have this new Pancake project, which is about a year old, and specifically targeting to develop a programming language that lends itself to writing efficient device drivers, yet be verifiable at reduced cost. And so we're looking for a system language that is memory safe. It's not managed. We don't want a bloody garbage collector in our device drivers. It's low level because we need to access hardware directly, and no runtime system or any smelly stuff like that. And so then, and of course, the whole point is we want a verifying compiler, so we can do any verification reasoning at the level of the semantics of the programming language, rather than something more low level like C or binary code. And so the idea is we use something that's already existing. And this was part of the learnings from the Cogent project. Is it's difficult to bootstrap a usable new language from scratch in a university environment. So instead, we're taking something that's mature and established. This is a KML language. Where did I mention that before? It's what we use in the verified initializer. So KML is a functional language. It's very high level. It's type and memory safe. It's got a garbage collector. But so a lot of bad stuff from a systems programmer point of view, but all the cool stuff. It's got the verified compiler and runtime. And it's a mature system with a mature and active ecosystem. It's got a nightmare of a compiler. So what you see here is the compiler phases. There's about 4 dozen of them. That's all done originally in the theorem prover. But that's okay, right? You just want to know that there's a compiler that translates your program. So with Pancake, the idea is we use the lower portion of the stack. So we get a compiler, not quite for free, but for relatively cheap. And so we have a new language that has another couple phases, only 3 at this stage, which basically accesses the lower level of and we use the lower level of the KML stack, and therefore we will end up with a verified compiler relatively quickly. And the cool thing is the Pancake compiler itself is written in KML. So that means we can use the KML environment to produce a verified binary compiler for Pancake. And then you can run it just like a normal C compiler. You don't have to mess with the theorem prover, etc. And it compiles directly to binary. So this is really cool. And it's a very active project. As I said, it started about a year ago. We are doing a few things in parallel, including doing some verification work on a toy serial driver. This is where everyone who wants to do drivers, they do serial drivers and then they stop. And that's pretty much all the other work. They stop there. This is for us, it's the starting point. And we have a prototype parser, which is, of course, the important part for having a complete compiler. We have almost completed the connection into the KML compiler. So this stuff exists, and just this step is still in work. And the compiler, the binary compiler bootstrap is in progress, and we hope this is going to be finished within a few months. And what's then the really tricky bits is the idea of shared memory. So CakeML, like a lot of these languages, lives in this ideal world where your program is the universe and all your memory belongs to you. And of course, in a real system, it doesn't belong to you. It's shared memory, whether that's device registers that you access and the device access and modify, or it's DMA communication with a device driver, or it's shared memory communication, which we need for our asynchronous transport layer. It all needs shared memory. And so that's sort of the conceptual, real significant contribution for Pancake, and that's will keep us busy for a couple of years. So we don't have anyone from the Pancake team here, but there is plenty watching in Sydney. And this is an active collaboration with some of the other folks in the CakeML space. So in particular, the Australian National University and Chalmers University of Technology, and it's also got support from TII. And then applicability. So far, pretty much we live in the ARM space, getting into RISC-V. x86, of course, is ugly and horrible, but it's reality. And so should be able to support that better. And here we have one project, which is the Makatia project, that basically builds an seL4-based secure VPN server for humanitarian organizations. And the company behind that is Neutrality. And so there we're getting onto server platforms. And it's basically requiring messing with low-level details, but also driving the device virtualization work. So that's funded by NLNet, which is a non-profit in the Netherlands. And then the real big long-term goal is the secure general purpose OS, which is where we hope to have something that has a generality that you can make a reasonable argument it will scale to something of the power of Linux, but with an overall verification story. And so there, it's got a complex structure where you need every connection needs to be explicitly authorized and can be revoked, etc. That's early days. We're working at prototyping core servers, and again, collaborating with Penn State and getting support from NCSC. Now, finally, sorry, 2 more minutes. I'm getting asked this question a lot, and it's really a frequently asked question. If you were to do it again, what would you do differently? And the good news is nothing major, because the major issues we had with the kernel originally, they all been solved now. There were really 2. The original version of seL4, this was before it was even released and completed, the verification completed, is you needed to always explicitly establish reply channels if you revoke a server. That's been taken care of by original reply capabilities in the MCS model, the first-class reply objects. And the second was, the scheduling was naive. That was understood. We wanted to solve one problem at a time. We kept time out. And that's now thoroughly addressed by the MCS model. So that's really good. So basically, all the big issues there has been solved. That doesn't mean there is no issues left to solve. And this is sort of my biggest annoyances I have with the kernel. The number one is the way map and unmap works. So the mapping operation in seL4 is an invocation of a frame capability taking an address space as an argument. Now, I know where that's coming from. It's a bottom-up view. It's an implementation view because the call actually modifies the frame capability, but not the address space capability. But of course, it does modify the address space. That's the whole point, right? So the user view is the opposite, that you invoke an address space giving a capability, a frame cap as an argument. Okay, you can say, well, this is just semantics and look. No, there's an actual cost to that, because the present model doesn't allow you to do multiple mappings in single system call, and similar for unmapping. So there's a real cost. And multi-frame operations are actually common. For example, particularly in embedded systems, you want to have real short startup times for applications, and they're very static. You can map the whole thing in right at the beginning. And we should be able to do this a factor of 10 faster than Linux, but having to map every frame with an individual system call is getting in the way. And then the new multi-server project has similar issues. So we expect some data on that quickly, pretty soon. And the other one has been a discussion about a year ago, lazy FPU switch. So the kernel only switches the FPU state on demand. Basically, when a context switch is done, the FPU is inaccessible. If a process tries to access it, it's a kernel trap. It switches the state and then returns and lets the app go ahead. These days, almost every application code uses the FPU. So the main advantage of this model of saving the context switching of the FPU is pretty much gone away. So there's no more benefit. But there's a cost, and that is an extra trap into the kernel. And the bigger cost is for those servers where you actually know they're not going to use the FPU. At the moment, unless you verify them, there's no guarantee they won't. And therefore, you have to make very pessimistic assumptions about their worst-case execution time. So I'd really like to get rid of that by having a more principled way of using the FPU. And of course, the principal way of dealing with any resource in seL4 is you have a capability that gives you the explicit right to access it. And then we can do all the reasoning fine. There's a few other issues under investigation that came up recently, like signaling, messing with the scheduling queues, which it shouldn't. Why do you need an explicit system call to acknowledge an interrupt when, well, I'm ready to receive the next interrupt? That should be an implicit acknowledge. Can we abort IPC operations by signals? There's more investigation to be done, so expect some discussion shortly. Okay, so where are we now? seL4 is the best already, and we're working hard to keep it that way, stay ahead of the competition, and I think we're doing well. It's got all the right ingredients, and most of them no other system has. It is real-world capable, we've shown that, but it's still hard work, and we're working on making that easier. And the core platform, the new driver framework, and the Pancake language are really important ingredients in that. And then can we get out of the embedded space? Not that there's anything wrong with the embedded space, but it's short of world domination. And so we're working on broadening there as well. And we have been defining the state of the art for the last 13 years, and we want to keep doing it. Thank you very much.
Thank you, Gernot. So we have time for a couple of questions from the audience. Please raise your hand and I will hand you a microphone so that folks online can also hear. Questions right here.
Hi. Hi.
Yeah, go ahead.
Hi. Yeah. You can hear me? Yeah, my name is Ivan. I would like to ask you, you mentioned this, that you use KML language as high-level language, but I remember that you have spent some effort on the Rust implementation. So can you give a few words? What's wrong with Rust?
Okay. What's wrong with Rust is it hasn't got a formal spec. It's sort of, people have been working it for years and years and years. There's been some candidate out recently. It's still a far way from what we want is a language where we can reason formally about code written in it, and the compiler takes care of the rest. Rust is a great language, and I know a lot of the community use it, and it's very useful, but it doesn't satisfy our requirements for verified application code.
Hello. Have you done any performance measurements on the impacts of the cache flushing on every context switch?
Yes, it's not every context switch, it's every security domain switch. So you don't need to do when you invoke a server because they're the same security domain. It's basically on the granularity of a time slice, 1 to 10 milliseconds, and it's negligible. The data is in the URSS paper.
It's a question about what's wrong with Rust to what's wrong with Spark.
show me it performs like what we need, then we'll look at it seriously.
Any other questions? Okay, well, if you have other questions, we'll have Gernot on stage later for the Ask Me Anything session with the rest of the technical steering committee for the seL4 Foundation. And so we'll have another opportunity. Okay, it's time for our break. We have a 15-minute